Hello, my name is Michael Alvarez. I am a PhD student of electrical engineering at the University of Puerto Rico at Mayagüez campus. I am part of the Laboratory for Applied Remote Sensing and Image Processing, LARSIP. I am going to present the work titled Analyzing the Effects of Pixel Scale Data Fusion in Hyperspectral Image Classification Performance. The outline of this presentation is composed of the introduction, classification problem, hyperspectral enhanced imaging, framework, deep learning techniques to enhance spatial resolution, classifiers, experimental data that is used in this work, results, conclusions. Introduction. Remote sensing is a growing area that is due to the high availability of data captured by different sensors in recent decades. In this field, the classification problem is an important topic. The main problem is the available reference data, or ground truth. That implies limited training samples, redundant features, and high dimensionality problem. In this context, for classification of hyperspectral images, there exist supervised techniques that take information from the reference dataset or ground truth and separate the data in knowing classes. Also exist the unsupervised methods that divide data by significant statistical difference in regions that not necessarily are the real classes of the reference map. Some common classifiers in the state of the art are the following: minimum distance, support vector machine, convolutional neural networks, and class-dependent sparse representation classifier. In order to improve the classification results, the fusion of data is adopted. The hyperspectral images of low resolution are fused with multispectral images of high spatial resolution. Then, a high spatial and high spectral resolution image is obtained. These kind of techniques are well known as pixel fusion. In this case, we use the long-short-term memory network as architecture for high spatial resolution enhancements. Framework section. The learning to enhance spatial resolution. In this case, we present the multi-scale long-short-term memory network and the classifiers. We present in a previous conference a multi-scale long-short-term memory network to pixel fusion. For that architecture, we take two hyperspectral images of high spectral resolution but low spatial and middle spatial resolution. Then, in pre-processing step, decompose the spatial and spectral parts, and we take only the spatial content of the high spectral pair. Then, that part and the multispectral image that has high spatial resolution is taken by the multi-scale long-short-term memory and produce a high spatial resolution and high spectral imaging. The classifier, as mentioned before, include the minimum distance method. The minimum distance takes the norm between points present in the dataset. In this work, we take the Euclidean distance, also known as norm 2. So the classification given by the method consists in finding the minimum distance between each test pixel and the mean value of the distance. The support vector machine is a method that is a generalization of linear discriminant analysis that finds the hyperplane that is largest separate in terms of the margin between classes. That is equivalent to solve the equation 2. In this case, X represents the training pixels. The class-dependent sparse representation classifier uses classification distance process like a k-nearest neighbor and then project the data in the span generated by the training pixels of each class. After that, compute a regularization process to minimize the error. That is, solve the equation 3. The convolutional neural network classifier takes the hyperspectral image separated in patches that are small spatially and preserve all spectral content. Then apply a series of convolutional filters that integrate the variability of two-dimensional shapes to get a categorical result that is the class of each pixel. Experimental data. The Indian Pines hyperspectral dataset is a well-known dataset. This scene was gathered by a very sensor over the Indian Pines in northwestern Indiana. It has a spatial resolution of 3.7 meters per pixel and consists of 145 times 145 pixels and 200 spectral bands. The reference classification map has 16 classes and is not all mutually exclusive. The Salinas hyperspectral dataset is another well-known dataset collected by a Viris sensor over Salinas Valley, California. It has a spatial resolution of 3.7 meters by pixels. The area is 512 times 217 pixels and has 204 spectral bands. The Salinas classification maps contains also 16 classes. The Enrique Reed hyperspectral image consists of 120 bands taken from a ISA Eagle sensor with the spatial resolutions of 1, 2, 4, and 8 meters. The Enrique Reed is located in the natural reserve area known as La Parguera in Lajas, in southwest of Puerto Rico. The image was captured by Galileo Group in 2007. There are 6 classes: mangrove, deep water, coral, sand, seagrass, and flower reef. Results. The results are separate, presenting first the comparison between the deep learning techniques to enhance spatial resolution, and then comparing between reference and the one technique, the long-term memory network. Comparing the overall accuracy. As you can see, we take 10 to 90, 30 to 70, 50, 50, and 75 proportion of data training and testing. If you take, for example, 10% of data training, you can see that the long-term memory has better results of classification. For example, when they use the class-dependent sparse representation classifier, they pass to 60 to 75, 15 points more. When you use the CNN classifier, you pass 53 to 70. And this behavior is consistent. So, if you increase the training data, you increase the classification accuracy. For example, if you take 75, for the long-term memory you have 90%, and the another technique has 71. Comparing now the average accuracy. It's the same behavior. For example, if you take 30%, you pass 47 to 88, more than 30%. Now, if you compare with the reference image, you have the long-term memory has better results. This happens because the hyperspectral cube generated by the long-term memory contains spatial details that were enhanced by the network. Salina hyperspectral dataset results. Comparing again the deep learning techniques to enhance the spatial resolution. So, as you can see, the results are higher in long-term memory network. This behavior is also consistent in the average accuracy, comparing long-term memory with the reference hyperspectral image. As you can see, again, the long-term memory has better results than the reference image. For example, take the 75 case. Using the class-dependent sparse representation classifier, you have 80%. Also, in the reference image, you have 64. Results for Enrique Reed hyperspectral dataset. In this case, the long-term memory has 12 points more than the CNN method. For example, compare the 10% of training data. You pass to 77 to 89, and in the average accuracy is the same result. Comparing with the reference hyperspectral image, you have now better results with the long-term memory. Conclusions. This paper presents the impact on supervised classification performance of 2D learning-based data fusion method. We have numerically proved that the long-term memory is a useful architecture to generate hyperspectral enhanced images compared with other architectures in literature, showing better results in classification accuracy. We also show that the long-term memory cubes are better to classify than the reference hyperspectral image. These results are showing a promising use of the long-term memory architecture to integrate multi-sensor data to improve classification. In a sequence paper, we show a decision fusion technique that further improves overall classification by combining the multiple classifier results, obtaining a higher accuracy per class. In future work, we propose a deep learning technique that performs image fusion to enhance spatial spectral resolution that integrates classification results in the network training. We thank Dr. Fernando Arias for sharing the CD as RC code and for useful discussion about classification problems in remote sensing. We also thank L3Harris Technologies, Space and Airborne System Division in Rochester, New York, for their support with the access to deep learning infrastructure to conduct our experiments. This material is based upon work support by National Science Foundation. Finally, the reference used in this work. Thank you.